Hey everybody, this is Husky again. We are moving right along with the next of my challenges from the Huntress 2023 Capture the Flag. This is Rock, Paper, Psychic. This is an exercise in binary patching, either static or dynamic. So let's go ahead and get right to it. So I've already unpacked the binary on the desktop. We have another executable here. And so if we run the executable, let's just go ahead and do that. Hi, I'm Patch, the telepathic computer program. Let's play rock, paper, scissors. I should warn you ahead of time, though. As previously mentioned, I'm telepathic, so I can read your mind. You won't end up beating me. Still want to play? All right, you've been warned. Enter your choice, rock, paper, scissors. So the point of this is that if you play rock, paper, scissors against a computer program that, quote unquote, reads your mind, or in other words, knows what you're inputting, it can always beat you, right? So it doesn't matter what we put here. I mean, we can try to fuzz, right? It's going to say that's an invalid choice if we don't put anything that's valid. So we can do rock. It's going to say, okay, ready, rock, paper, scissors, shoot. And then when it shoots, it's going to say, I choose the one that counters whatever you chose. You chose the one that you chose, and then I win. So the computer always wins. So in this case, what do we do about this? So we can try to play. We can try to play as many times as we want, but the computer's always going to win. So instead of that, well, remember that we have the binary on our computer, right? And so we are in control of the bytes of this binary statically as it resides on disk, and we're in control of the bytes of this binary in memory when it's actually running. And so who's to say we can't make this program do what we want it to do? And one way that we can do that is by binary patching. There are two main ways that we can do this. We can do this statically, right? Just go in and actually edit the bytes of the binary on disk and then run the program and have it, perform whatever we wanted it to do. Or we can do it in memory when the program is running. So let's start with the static side of this. So I'll go ahead and open up Rock, Paper, Psychic in Cutter, which is our disassembler, at least the one I'm going to use. And we can load this in write mode, and that's very important. So we can actually change the bytes of the binary as we see fit. So it's going to do its analysis, and then it's going to open up our disassembly view. All right, great. One thing to note in here, debug symbols have been left in. So you can see on the side here, we actually have nice, convenient, readable function names. And we are, in fact, working with a NIM-compiled binary. And we know this because we've got three specific modules here, NIM main inner, and NIM main module. Let's go ahead and follow this down. We can actually go to the graph view. I think that's probably the easier way to visualize this. So effectively, NIM is a little weird in its binary structure. It's got three wrapper functions around what we would consider to be the actual main function of a binary. And so what we want to start is we start at NIM main. We can then go to NIM main inner. And basically all NIM main inner does is initialize NIM main module. And so NIM main module is where our jump to the actual main function begins. So as we work through this program, we basically want to figure out a couple things. So the way to get the flag in this program is to win against the computer. So ostensibly, there's going to be some point in this program where the evaluation takes place, whether you won or the computer won. And then, as a result of that, it's going to run the part of the code that actually happens when you win. Now, the way it's set up now, we're never going to get to that part of the code because the computer always knows what you're picking, and it will always be able to pick the corresponding counter to whatever you're picking. But in any case, if we go find the functions in the program where we see that the getComputerChoice function is called, the determineWinner function is called, and then there's a split in the code path. There's a jump if not equal to. We'll go over what that means here in a second. On the right side of the graph, so everything I'm looking at right here, the playerWins function is called. And on the left side of the graph, the computerWins function is called, and then the rest of the program, which basically prompts you again if you want to play again. We will never get to this side of the code. It exists, but we will never get there because the winner is determined dynamically when this determineWinner function is called. And our idea here is to patch the binary to get here. The first way that we could do this is to identify the memory offset in this program where the call to player wins exists, which is right here. We can copy this address, so 0x00416C6A. That is the offset memory location of where we actually call player wins. And if we go all the way back to the very, very start of the program, before any of the logic has checked to see if we're the actual winner or the computer wins, we have another call up here and a NOP that follows that call. So who's to say we can't just insert the call or maybe put a jump instruction here to jump right to that location? So that is one potential solution for this challenge, is to statically patch, take that location of the player wins function and patch it right into the earliest part of the program that you can get to. I like to just do it at the bottom of these call graphs because I know that it's about to jump somewhere, and that's a convenient place to do it. You can even pick out something like the JE right here and just patch that location. So if you know that you can reach this point in the code, if you patch that location with the memory location of the win condition, then that works as well. But let me show you the other way to do this, and I think I like this way a little bit better. Let's break out, I believe this was a 64-bit program, if I remember correctly. So let's break out x64 debug, and let's open Rock, Paper, Psychic in x64 debug. And I think it's could not read file because it's probably open in Cutter. So let me just go ahead and do that and try to open it again. Okay, there we go. Looking good. So the idea here is that we need to track down the memory location of where these calls are taking place. And one easy way to do that is to correlate it from the memory offset locations of the binary when it's actually loaded in memory. So a quick way to do that, actually, we will open Cutter back up, and we can actually just open it up in read mode. So we'll open up Cutter, and we'll get our binary, our Rock, Paper, Psychic binary back into Cutter. We can just open that up right again. We don't have to load it in write mode again. We can just open it up in read mode. Because all we really want to do right now is track down the memory offset location to cross-reference that inside of x64 debugger. So let's go back and find, I probably should have just done this ahead of time, but let's go ahead and find main, the system main _ main function. And so what we want to do is find the area where the determination of the winner is made. So 0x00416BDF. So let's copy that memory address and go right over into our memory location. What we want to do is run the program. If you just run this until we're actually in the module of Rock, Paper, Psychic, basically when a program is loaded into Windows, it has a bunch of preamble, it loads NTDLL, it loads a whole bunch of other DLLs. But when we get to the actual binary itself, when it's loaded into memory, this is where we want to be. Hit Control G. This is going to bring up our locator to find an expression. In this case, we're pasting in a memory location. And we find the location of the call to the determine winner function. So here we are. Now, this is a lot harder to track because we're in the debugger now, but basically we are running through every instruction in the program. And let's go ahead and F2 set a breakpoint on that location. Now, the important one here is actually this instruction right here, test ALAL. Essentially, Rock, Paper, Psychic will run the determine winner function. And the determine winner function essentially says, did the player win? If true, return something into the contents of the EAX register. In this case, that's a single bit value, so it actually doesn't even need the full EAX. It can just use the AL, the A low register. So to recap, call determine winner, which we're looking at right here, which we've cross-referenced with in here. So we're looking at the same two instructions from these two memory locations. Call determine winner and then test ALAL. The test instruction will set the 0 flag in the registers. If we scroll down on the register side over here, the ZF is the one that is of importance. This is the 0 flag. So let's set a breakpoint on that test ALAL. In fact, we can take that breakpoint off. All right, so from the top, let's go ahead and run the program again now that we have our breakpoint on the testing of ALAL. And so we do have to input any kind of choice here. Again, it does not matter. Now it's going to do rock, paper, scissors, shoot. I choose paper, you choose rock, and then we hang here. Now, the important part here is that the test AL will set or not set the zero flag. We want to go one instruction after that, because whatever this is set to, it actually, we don't want that to be the result. In our case, we want to flip the result and invert it, right? We want to change that. Basically, this test AL says the computer wins. If we flip the zero flag, we're now saying, no, the computer's not winning, we're winning. So now that the zero flag is unset, we are going to take that jump. And so we do the step over, and we can go ahead and step over until we get this output. And it says, you won. Wait, how did you do that? Cheater, cheater. And then the flag is printed out right there. So that is Rock, Paper, Psychic. That's a lesson in binary patching. You could have either approached that statically and patched the bytes as they reside on disk, or you could do that little zero flag manipulation, and that is the challenge. So that is Rock, Paper, Psychic.